Imagine playing snooker. You strike the cue ball, it hits a red, and the red drops into a pocket. Predictable, logical, and exactly as you'd expect. This is the world of classical physics, certainty, order, and Newton's laws. But beneath this familiar surface lies a realm that defies all logic, the world of the very small atoms, electrons, photons. Here the rules change. Particles don't act like tiny snooker balls. They can be in multiple places at once or vanish and reappear elsewhere. This is quantum mechanics, a world built on probability, not certainty. Even the pioneers like Bohr and Heisenberg were unsettled by its implications. Instead of knowing exactly where a particle is, we can only talk about the likelihood of finding it somewhere. This shift from certainty to probability is what makes quantum physics so strange. Yet, quantum rules shape everything. The solidity of your chair, the light from your screen, even your thoughts. To understand the universe, we must embrace this weirdness and explore the quantum world. Here, the impossible becomes possible. At the start of the 20th century, physics seemed complete. Newton and Maxwell explained the universe with clockwork precision. But odd experiments began to break this tidy picture. Max Planck, studying blackbody radiation, proposed energy comes in discrete packets, quanta. Einstein took it further. Light itself is made of quanta, or photons, explaining the photoelectric effect. Suddenly, light and matter could be both waves and particles, a radical break from classical thinking. Quantum mechanics emerged, a world of jumps and probabilities, not smooth paths. Electrons don't orbit like planets. They exist in clouds of probability, with only certain allowed energy levels. Moving between these levels requires a quantum leap, instantaneous, not gradual. The quantum world is jumpy, unpredictable, and fundamentally different from what our senses perceive. This new physics changed our understanding of reality forever. One of quantum mechanics' strangest ideas is superposition. In our world, a coin is either heads or tails. In the quantum world, a particle can be both at once until we measure it. It's not just unknown, it's truly in all possible states simultaneously. The universe, at its core, embraces ambiguity. Then there's quantum tunneling. Imagine a tennis ball hitting a wall. It bounces back. But an electron might simply appear on the other side, as if it tunneled through. This happens because a particle's position is a wave of probability, and part of that wave can leak through barriers. Quantum tunneling isn't just a curiosity, it's essential for life. The sun's nuclear fusion, which powers all life on Earth, relies on tunneling. Without it, the sun wouldn't shine. Superposition and tunneling show us a world where particles defy common sense. These effects are real, measurable, and shape the universe. The quantum world is not just weird, it's vital. Our reality depends on it. The double-slit experiment reveals quantum strangeness in action. Fire electrons at a barrier with two slits. Behind it, a screen records where they land. With marbles, you'd see two bands. With electrons, you get an interference pattern like waves, not particles. Each electron seems to pass through both slits at once, interfering with itself. But if you watch which slit it goes through, the pattern vanishes. Now it acts like a particle. The act of observing changes the outcome. It's as if the electron knows it's being watched and chooses a single path. This experiment captures the central mystery of quantum mechanics. Particles behave as waves when unobserved, as particles when measured. The universe is fundamentally altered by our observation. Reality at its core is shaped by the act of looking. Quantum mechanics forces us to rethink what it means to know something. Quantum mechanics isn't just theory, it powers our modern world. Microchips, the heart of every computer and smartphone, rely on quantum rules to function. Transistors, lasers, and even GPS systems all depend on quantum effects. Lasers work by stimulating atoms to release photons in a precise quantum way. Atomic clocks, essential for GPS, use quantized energy jumps of electrons. MRI scans, which let us see inside the body, are based on quantum principles. Now, we're building quantum computers, quantum cryptography, and ultra-sensitive quantum sensors. By embracing quantum strangeness, we're inventing the future. The weirdness of the quantum world is not just a curiosity, it's the foundation of our technology. The impossible has become practical, and the future is quantum.